Hi, my name is Tomer, and I'm working in IBM Research here in Israel, and I'll be speaking today about arrays in the database CRDT framework. This work was conducted as part of Arik's internship here in Israel in our Haifa research lab. I'll start with a quick reminder about CRDTs. So in the CRDT framework, we have a bunch of replicas where users can modify the data stores in the replicas concurrently, and then the replicas do some synchronization, and eventually they reach the same state. We have all the many examples of existing CRDTs. For example, multi-value register, last writer wins, or grow-only counter. And these CRDTs are actually used in many production-level NoSQL databases. We have three main kinds or families of CRDTs. The first one is called the state-based, in which the entire state is sent over during the synchronization phase. And this state is a joint similarities object. Then we have the op-based approach, in which an operation is sent during the synchronization. And finally, we have the delta-based CRDT approach, in which not an op is sent and not the entire state is sent, but rather a small partial state is sent, which is called delta. And this partial state or delta is typically small. And this is the main focus of our project. So in the database CRDT approach, we have something called dots. So a dot is basically a tuple of replica ID and event number. Conceptually, the dot I and N identifies the nth event that occurred in the replica I. Then we have something called dot store, which is a data structure for storing all current dots available in the replica. And then finally, we have a causal context, which contains all dots ever observed by the replica, and it does so in a compact manner. The motivation for our work is semi-structured documents, namely JSON, XML, and more generally, NoSQL databases. However, the main nested object in the delta-based CRDT framework so far is a map. However, maps alone are not enough, not sufficient for constructing all semi-structured documents. For example, in order to construct a JSON, as we can see on the left, we also need arrays. We consider the following maybe natural requirements for an array in the semi-structured document. The first requirement is the ability to have arbitrary nesting, meaning the ability to have array, inside the map, inside the map, inside an array, and so on, in an arbitrary long chain of nesting. And the second requirement is the ability to be able to move the elements from one position to another, where users can modify these positions concurrently. In our work, we managed to construct two delta-based CRDT arrays. The first one we call remove wins array, and the second one we call observe the removes array. Their common properties is that both arrays, we have arbitrary nesting. In both arrays, we can move elements around concurrently. And finally, in both arrays, we don't store tombstones. The main difference between the arrays is their semantics. Specifically, the way they handle a concurrent operation on the array elements, and we consider the following three operations: an update, a move, and a remove. In this process, in our work, we also constructed a new dot store, that structure which we call a com.pan. And this is actually the main building block in our constructions. So let's talk about the semantics of our arrays. We basically extended all of the existing semantics, the remove win semantics and the observed remove semantics to handle also a concurrent move operation. So in the first semantics, in the remove wins array, a remove beats concurrent a move and an update, where when you do concurrently an update and a move, these both are preserved. In the array semantics, observed remove array, in the observed remove array, the order of precedence is as following: an update beats remove, which beats a move, meaning that an update overrides both removes and moves, and a remove overrides concurrent moves. On the left, we can see an example that these two replicas start from the same state, and then in one replica we update some element, where in the second replica we do a deletion or removal of that element, and then after synchronization, in the all semantics, the element is updated and moreover is kept in the array, where in the remove wins semantics, the array element is deleted. Our main building blocks is two already existing dot stores, .map.store and .fun.store. And we also constructed the new .store, which we call com.fun, standing for a composable .fun. This dot store is conceptually some sort of combination between these two dot stores I mentioned. The state of the com.fun is a mapping from dots to some dot store. And the main property which we use in our construction is that when you concurrently update an element, so you update some dot store, internal dot store, and you remove this item, so you remove the key, the dot that points to that dot store, altogether that item is deleted from the com.fun dot store, and the update is disregarded. So in the first construction of the remove wins array, the com.fun is the top level dot store. And an array element is uniquely identified by the creation event or the dot of the creation. This way, when you do an update or a move, which is essentially updating some dot store pointed by the unique identifier, and concurrently you do a deletion, by the property of the com.fun, this item is removed from the underline com.fun and therefore removed from the array. In the observed remove semantics, the top level dot store is a dot map. And again, an array element is uniquely identified by the creation event, which is again a dot. The most interesting part is the way we store the position identifiers, and we store them in a forest structure, as we can see on the left. On the left, we can see a forest in which in every phase we only have one tree, but essentially we can have many trees. And the position identifiers themselves can be any reasonable enough position identifiers, specifically position identifiers in which the order of the relative ordering is stored in the position identifiers themselves. For example, Lagut, LSEC, and so on. So the trees are of height 3, and in an insert, we add a new tree. As we can see, we added a new tree. On an update, a new tree is added, inserted. So we insert a new root, and the previous one is removed. And during a move, only the intermediate level is updated. And in particular, you can see that we switch to a new position. On a remove, the entire all roots, all trees are removed altogether from the forest, and the item is deleted from the array. Yeah, so that's it. Thank you all for listening, and I'll be happy to answer any questions regarding the presentation or the paper, life in general. Thank you.